everyone. Welcome back to the 129th episode of the Qiskit Live Seminar Series. I am Maria Violaris, and I am your host for today's talk by Andrew Vlasic and Sal Certo. I work part-time with the Qiskit community team, mostly on making video content for the Qiskit YouTube channel, alongside my PhD at the University of Oxford. Now, while we wait a few minutes for everyone to arrive today, I'd love to know where you are all joining us from. So please use the live YouTube chat to tell us where you're joining from today. This live chat will be open throughout the seminar, so please feel free to drop in questions there at any time and comments for me or our guest speakers, and we can discuss them. At the moment, I am in Bristol in the UK, where it's just past 5 o'clock. So let's see. We have someone joining us from San Diego. We have Portland. We have near Eureka, Montana, from Melmac, India. Already a huge range of places. So great to see so many people joining us from different places. We also have Vancouver and Germany too, and Ecuador. Lots of places. So thanks all for doing that, and please carry on telling us where you are all joining from. So we can slowly get started in introducing today's speakers and getting started with the seminar. So for everyone who's just joined us in the last few minutes, hello and welcome. I'm your host, Maria Violaris from the Qiskit community team and University of Oxford. This seminar happens live every week at 12 p.m. Eastern Time. All the episodes are recorded, and you can find them, all of the past episodes, on the Qiskit YouTube channel, but you can only ask your questions in the comments if you join us live. Remember to subscribe to the Qiskit YouTube channel to get regular updates about new seminars and lots of other quantum computing content. So I'm here with today's speakers, Andrew Vlasic and Sal Certo from Deloitte, and they'll be talking about a joint work they did along with researchers at IBM Quantum. Dr. Andrew Vlasic has a PhD in mathematics and extensive experience in fundamental and applied research, both in academia, the Department of Defense, and industry, including the Bank of America. Since joining Deloitte, Andrew has specialized in fundamental quantum algorithms, making advancements in quantum machine learning and in optimization problems. Sal Certo is an experienced data scientist helping companies solve their hardest problems using the latest technology. He has experience in deep learning, graph analytics, and operations research, and is using the latest quantum algorithms to provide state-of-the-art solutions in optimization and machine learning. So welcome to Andrew and Sal, and I will now hand over to our speakers. So feel free to get started.
All right, absolutely. Thanks a lot, Maria. So yeah, good morning, good afternoon, everyone. Like Maria mentioned, this presentation is on some of the joint research we conducted with IBM Quantum, and it's on conditional generative models for learning stochastic processes. Great, so the agenda for today's presentation, we are going to provide an introduction to generative models. Obviously, there's a lot of hype and enthusiasm around generative models currently with things like ChatGPT and other large language models being deployed today. But in general, if generative models are trained adversarially, they're known as generative adversarial networks. And so we're going to go into what exactly those are. If we apply them to the quantum setting, what sort of benefits can we realize, and how does their complexity scale in a quantum GAN? We're then going to introduce our research, which is a conditional quantum generator. And one of the main applications of this is in pricing financial derivatives, or other quantum Monte Carlo simulations. And so for that, we're going to provide a brief background into options in financial derivative contracts, specifically path-dependent options, like the Asian option. And then from there, we're going to go into exactly how we use our method in a subroutine as part of this quantum Monte Carlo simulation to price these financial instruments, and then go over the results and next steps. All right, great. So next slide, please. Great. So like I had mentioned, generative models are, there's a lot of enthusiasm around today, but they have been around for quite a while. And they really can be as simple as predicting the next word in a sentence, or they can be very complicated, like ChatGPT. But in general, a generative model is any sort of machine learning framework that creates new data instances based on the likelihood of that instance. So they're really trained to learn the distribution of a random variable, or the conditional or joint distribution of multiple random variables. And so they're not just large language models, but they could be autoregressive models, autoencoders. And again, if they're trained adversarially, those are what are known as GANs. In the bottom there, we just have a simple diagram or architecture of what a generative model could be. So for instance, if we want the model to create new pictures of horses, we could have it trained on a catalog of different images of horses. And what we would do is we would feed it then some random noise in hopes that it would create a new picture of a horse based on the training data. So it would learn not only the distribution of the images it was trained on, but also the joint distribution of all the pixels within each image. Next slide, please. Great. So the motivation for looking at generative models and seeing how we can apply them in the quantum setting is that there's a variety of quantum algorithms that rely on what's called state preparation. So how do we load certain distributions into a quantum system or register, and how do we load it efficiently? So on the right there, we have a picture of what looks like a normal or log normal distribution that's loaded onto a quantum register. And so anytime you would measure or sample from this quantum system, you would get a certain bit string or state that corresponds to the number at the bottom there, with a certain probability of this distribution. And so the goal is to construct a circuit or a series of gates that whose quantum state then represents that distribution as close as possible. Now, there is an exact method for doing this, and it's known as the Grover-Rudolph method. So it provides some instructions for how you can construct gates to efficiently load these distributions onto a quantum register. However, there's two main drawbacks to the method. The first of which is that you have to know the distribution beforehand. And so that kind of really defeats the purpose of things like quantum Monte Carlo simulations, where the entire idea is to integrate over an unknown function or distribution. The second main downside is that if you have more than one distribution, you're going to need more than one quantum register to store that distribution. And so in things like stochastic processes, where we're looking at different paths of a random variable, that can really quickly get out of hand and really tax the resource requirements for the quantum circuit. So our motivation was to really try to address that second bullet point of how can we efficiently load multiple distributions in the context of state preparation onto one quantum register. We also think that our conditional generative model could be extended to be trained adversarially, which could also address that first point. If you don't know the exact distribution, but you have some sort of samples of the data or the training data, you could train that adversarially and also learn that unknown distribution.
Thanks. We have a clarificatory question about the previous slide. So if we do not have noise, it generates images similar to the training data, is the question.
Oh, on the previous slide.
Yeah.
Yeah, exactly. So that noise is really important. So we're going to feed this generative model a random noise vector because we want new data instances. Correct. If we didn't have that random noise, it would really just learn all of the training data and really just mimic back to us the images we've fed it.
Mm-hmm. Cool, thanks.
Mm-hmm. Okay, so now Andrew's going to talk about quantum GANs and some of their benefits and complexity.
Great, thank you, Sal. So as my colleague Sal noted, our method utilizes a generator, but this can be easily extended to adversarial networks. So given this, we thought it would be prudent to go over the inner workings of a GAN, look at the classical GAN characteristics of that, and the characteristics of a quantum GAN, and then compare against each of those to really display the importance of using a GAN within the quantum setting. But before we do that, let's go over exactly what the inner workings are. So GANs in general, they have three parts. There's the real data, the generator, which is tasked to, as Sal noted beforehand, to generate different images or different instances, or essentially to approximate the underlying distribution of the data. And then the discriminator, which is tasked in identifying what synthetic data is and what real data is. And then the training goes as follows, and it's important because it's very sequential. First, the discriminator is then fed real data, and then learns what real data is. Those parameters are updated. Then it's fed fake data from the generator, and then the parameters are updated so it understands what fake data looks like. And then that synthetic data is generated again, and then fed to the discriminator. So then the generator learns from the discriminator what it believes fake data looks like, and so it can learn against that. And then those parameters are updated all accordingly. And because of this, it's important for both the generator and the discriminator to both learn what their tasks are precisely at the same time. And if you're wondering if this is a game, it's precisely a game, and it converges to a Nash equilibrium. So it's very interesting. But for the quantum setting, there's an extra piece. There's an ancilla qubit that is used to then test the state fidelity. So the output of the discriminator and the output of the generator or the real data. And then with the Hadamard swap test, the state fidelity can be calculated very quickly. And because of this extra piece, as we will see, you really do get an advantage using quantum. Next slide, please. But with this in mind, we really have to consider why precisely should we move from the classical setting to the quantum setting, especially given all the tremendous amount of advancements that GANs have made, and they've made very impressive advancements, but it's all done classically. So essentially, why quantum? Well, as Sal noted, and as actually the question actually noted, you need a random vector to then seed the generator, and then look at that output. Well, that random vector has to be created by some random number generator, so a distribution has to be assumed a priori. As one might believe, being a machine learning expert, you need a tremendous amount of data to train a nice, robust statistical model from the generator. And I would be remiss if I didn't note that there have been advances with the amount of data that's needed to train a robust model, but this is the particular use cases. And finally, for all of us who've actually attempted to train a classical GAN, vanishing gradients are they're just a pain to work with, right? And they're quite prominent in GANs. This is because GANs tend to need deep and wide neural networks to be able to extract that information from the data, to then be able to give the discriminator, well, the generator, the proper information needed to give you a nice, robust statistical model. But because of this state space being classical, the state space is non-convex itself. right? And all of us have been working with machine learning, have definitely dealt with those energy wells, right? It's not precisely the optimal point, but it's almost there, and we have to kick ourselves out of it in some way, right? This is very prominent in GANs. And then finally, once the dimension of the data increases, the number of parameters needed is going to grow polynomial. It could be linearly, but it tends to be polynomially, and then potentially exponentially. And this is because as the dimension increases, you need a deeper, definitely wider, but a deeper neural network. So you need to add more layers in there to be able to extract that information out of the data. If anybody's curious about this, the only thing I've seen mathematically is this wonderful paper from 2018 called Tropical Geometry of Deep Neural Networks. Although they just look at neural networks applied to logistic regression, it really does emphasize the importance of having a deep and wide neural network to be able to extract that information out. Okay, next slide, please. Well, with this in mind, well, let's compare this against the quantum circuit, and then the complexity with a quantum circuit when one has a GAN strictly within a quantum circuit. Well, as was noted, when you have your vector, right, which is needed to see the generator, and you have an a priori distribution that one has to assume. Well, in the quantum setting, where you have inherent randomness with qubits, which is fantastic, and actually has been shown to give you advantage over a random number generator. Also, as one way imagine, since you tend to only solve for one parameter per operator when you're in a quantum circuit, it does require a little bit of data. This analysis is actually rigorous in the wonderful paper that I can't think of at the moment. I apologize for that. Probably should put in my notes. Right, and then also so thinking about vanishing gradients, right? While vanishing gradients are prominent in quantum circuits, they are not seen in shallow networks, and this is really important here to think about when we're actually creating a neural network architecture within a quantum circuit. So going back to what I said beforehand about the GAN being strictly within a quantum circuit, and that variational piece done outside of it, because of this, the state base is convex, and this is exactly the Kukutani fixed point theorem. And because we have a non-convex state space, convergence is faster, and we actually get to that optimal point to really give us that robust statistical model. And also, and this is more of a post-it at the moment. When you have the degree of the dimension of the data increase, you're going to tend to have linear in polynomial growth as well as linear growth in the number of operators within your quantum circuit. And this is believed because you have the complexity of the data is actually captured through entanglement better than within the classical setting.
All right, great. Thanks, Andrew. So Andrew, you had mentioned that the biggest advantage comes when both the generator and the discriminator are strictly within the quantum circuit. But there are some implementations that do have a classical discriminator. Do you realize all of these benefits with that hybrid approach?
Yes, absolutely. There's been a lot of work on looking at the neural network architecture and then putting in pieces of the quantum neural network within the larger structure, the neural network structure. And an example comes to mind from a few years ago, actually from IBM, where they used the neural network architecture applied to logistic regression for binary classification. And they used the first part of that neural network architecture to be strictly within a quantum circuit. And then the last piece is that extraction of information so it can be mapped down and then finish up the training within the logistic regression, and actually showed an increase over the classical setting within that. So one may be able to see advantages by including quantum circuits within their network. However, as was noted in the case of GANs, and through our own experiments, we've actually seen a tremendous advantage having the neural network architecture strictly within a quantum circuit.
Absolutely. Yeah, great. Thanks, Andrew. So I think, as Andrew alluded to, there's a lot of different approaches to GANs, and especially in the classical setting, there's a lot of different extensions or flavors of generative models in general. And one of them is called a conditional generative model. And so, in essence, a conditional generative model is not that much different from a normal generative model. But here, the idea is for the model to learn not only a high-dimensional probability distribution, but a high-dimensional conditional probability distribution. So, for instance, on the architecture on the bottom, instead of just feeding it pictures of certain types of animals, we could also label those images of what, for instance, animal they are, and provide that information to the generative model. So then when it comes for time for inference or to generate new data instances, we could not only provide the model with a random noise vector, but also the conditional class of which we want to sample from. So in this case, we could specify, give me a new image of a fox or a crow. And so that's actually pretty powerful, because what you can end up doing is start to mix some of these conditional classes. So in the top right there, instead of just generating an image of an actor, you could say, give me that picture with him having blonde hair or her having red lipstick. Or even back to the animal pictures, give me a picture of, a half fox, half crow animal. And it may spit out, a pretty gnarly animal that maybe you wouldn't necessarily want to look at. But so we took this idea of these conditional generative models and started to think about how we would construct them in the quantum setting. So if we go to the next slide, we can see just an overview of what exactly this would look like in terms of an adversarial network. And again, it's pretty simple. We would instruct the generator with a conditional class, and it would generate samples from that conditional distribution. We would also then provide the discriminator with that class label that was fed to the generator, so that the discriminator is not only tasked with determining what data instances are real or fake, but also real or fake depending on the class label. And so this is a pretty powerful extension. And on the next slide, we're going to go over the exact circuit structure we use for our conditional generator. So we have two main registers here. The first register is a generator register, and it is tasked with outputting the distributions of interest. Our second register is the condition register, and that's where we hold all of the conditional class labels that we have. And really, they can just be thought of as initializing that register to a binary number that represents, for instance, the index of our condition. We utilize two main ansatses for this circuit. The first of which we call the conditional map, parameterized by theta. And so these are just controlled Z rotations on the generator register. And then that's followed by another ansatz parameterized by theta. And here we just took a very simple approach of using a two-local circuit. And so a two-local circuit is standard in Qiskit, and it's just a series of rotational Y gates followed by controlled Z gates. And we did this for about 2 layers with full entanglement. And so importantly, the number of parameters, at least for alpha, grows as the number of qubits in your generator register times your number of qubits in the condition register. But importantly, you can hold a lot of conditions in the condition register. And by initializing that to the one of interest, the generator register would then output that specific conditional distribution. And so hopefully, in a few slides, we're going to go into why this may be useful. We think this has applications in various areas, but specifically related to finance and quantum Monte Carlo simulations. This will be a very powerful framework at which to price some of these more complex path-dependent derivatives. So for an overview on those derivative contracts, Andrew's going to provide the necessary context.
Great, thank you, Sal. Oh, I'm sorry.
Yeah, just a couple of questions have come up in the comments. One is that it was mentioned that complexity within the data is captured better by entanglement than classical methods. Could this be elaborated upon or some reference given, as it sounds quite interesting?
Well, I apologize for this. I actually said post it, right? This is what we believe to have happen. We don't really have that yet, but as one can believe with the entanglement, right? You just have these neural networks. They just map the data from different dimensions with the various weights. While entanglement, well, it does have that weight. It does put everything in that superposition with that respective probability, and with that. And because of that, because you have that extra complexity with the superposition and the various different probabilities, we believe that especially with our from our experiments, that when you solve for these parameters, you're solving for a number of different cases at once, and so you're able to not have to add extra layers into the circuit itself to extract that information out. It's just done quite naturally through the entanglement. Sal, do you have anything to elaborate on with this?
No, I think you answered it well, Andrew.
Cool, thanks. And another question is, if a classical GAN takes weeks to learn, then comparatively, how quick does a quantum generator learn?
Yeah, I guess that depends if you're measuring the time on the wall clock or from a number of iterations perspective. So that it is a very great question. And it's tough to answer. I think there is indications that quantum machine learning models can learn on less training data than classical in some instances. So from a complexity standpoint, it would make sense to believe that we could perhaps train these a lot quicker than we could classically. And that is the hope, that even if we have a really large classical machine learning model, perhaps by inserting a quantum layer in the middle of it, we could cut down on the number of, the depth of the neural network significantly to leverage some of these unique quantum properties.
Cool, thanks. And one more question is, I heard that quantum states can't be copied, so I think you can't make residual networks where you add some input state at the end. So what models are you limited by using quantum mechanics? So I guess, does the inability to clone quantum states affect things in this context?
Yeah, in this context, it does not affect our application or use case.
Yeah, it's a great question, but it's just not applicable. It probably deserves its own seminar. So. Cool, thanks. Yeah, we can carry on for now. Thanks. Great. So before I jump into options, I've been thinking about applications. Do you have any particular use case besides pricing financial derivatives that we can apply this method to?
Yeah, it's a great question, Andrew, and I have been thinking about it. So we did come up with this with the specific purpose of pricing financial instruments. I do believe there's probably other applications it could apply to. I can imagine, for instance, if you wanted to generate MRI images of different parts of the body with different abnormalities, mixing some of these conditions to create new images that have maybe a few abnormalities or whatnot could be helpful. I guess I would say anytime you'd like to maximize your efficiency of training these models, mixing the conditions, this could be a very valuable framework. And then I would also just end by saying that one of the reasons why we're giving this presentation and we have our research out there is so that the community itself could start to think about those questions. Where else could we apply this to? What does this mean for my use case, and how can we extend it? So,
wow, yeah, well put. Well put. Thank you. Okay, so now let's jump into options here. Okay, so why options? Why did we focus on this and as this particular use case within our paper? Well, options, they're tangible, and they're also a well-researched use case especially for pricing financial instruments. I mean, this is there's just a plethora of knowledge out there. But to understand the dynamic of an option and what exactly a call option under an agent pricing contract is, right? I mean, these are all buzzwords, so let's dig in deep to what precisely all this means. Well, the options, right? These are quote unquote financial instruments, contracts, who's based on some type of underlying security asset, or you know, for example, a stock. And option contracts, they give the right of the holder of the contract to buy or call or sell or put this particular asset, and but the underlying holder is not obligated to act on the contract. So before we get into the pricing in the next slide, and the purpose of option contracts in general, let's go over the different types of these contracts. So there's the standard kind of vanilla contracts. They're called the American and European. The American option is the contract that's stated that has an expiration date, but the holder may choose to enact that contract at any time before the expiration date of that contract. The European option is very fixed. It only at the expiration date may the holder of that contract execute that contract. And with both options, the price of the security at that time is going to dictate the worth of that contract. So for two quote unquote exotic options, you have the Bermuda contract, which is similar with the American and European, hence the name Bermudan. There's no doubt, there's no level of creativity when people name these things. This contract has a fixed number of times until the expiration date, and when the whole of the contract may be able to execute the contract, and then the worth of the contract at that time is going to be the current price of the security. But for our case, for this use case that Sal and I went over, the Asian contract. Now, this is a European contract style, in that one can only the holder of the contract can execute this contract only at the expiration date of the contract. However, the price of the contract is actually the average price of the underlying asset, such as a stock, over the entire lifetime of that contract. So to get an idea about the payoff the one would have holding these contracts, the figure on the far right shows, you know, it's linear, not necessarily linear, but with respect to the price of the security at that time, then that would be the profit or expected profit that one would think with the contract would actually give to an individual. So let's move on to the next slide and discuss exactly how to price these. All right, so let's take a step back and discuss why options were created in the first place. So let's give the example of somebody, they bought a stock for $18 a share, and then the current price of the stock, let's say, is $21 a share. So that's a nice profit. $3 a share that's a nice profit. However, you know, the person holding these stocks would expect the price to go up, but one would want to mitigate the potential of the stock price going down, and then you would lose on what you assumed would happen if you would have sold these stocks at that time to get that $3 share profit. So then one would create a contract, an individual would create a contract, and say they would sell it at $20 a share instead of that $21 a share. And then so that it would be attractive to people to purchase this. And then we would say at that time of that this contract would end in 2 months, and at that time, I will sell you this stock at this price, at $20 a share. But right, so this is very attractive across the board, especially if that price just increases to say $30 a share. But if I'm going to sell this contract to somebody to hold so they can have the ability to execute it at that expiration date, right? Going back to the again the European call option, then I would want to be able to price it in such a manner where I want to get as much money as I can out of selling this contract. And this is quite attractive. So so be able to price this contract at any time, because one can buy this contract and then sell it themselves. Because if it's up to $25 a share, and this person doesn't necessarily want to purchase these to purchase these stocks that the contract is there for, then he would want to sell that as well. And the way to price it would be the price at that time, that's the S sub T, minus that strike price, or the price that is on the contract, or zero, because you wouldn't want to execute this contract if it's definitely right less than the strike price, because there's just no value, right? So with this in mind, and this is the bullet on the top, the second bullet on the top. If you look at the second bullet on the bottom there, that's how one would be able to price as an agent option, with the time out. So this is the time that it starts all the way out to the expiration date minus that strike price. Well, as one would believe, just especially looking at these prices and how chaotic they are, especially with the number of the influences out there that actually affect the stock price, we would have to get a better idea of how to exactly sell this, so that not only is it fair market, but we do actually capture the underlying dynamic. And this is where two authors back in the 70s, Black and Scholes, they said, okay, well let's put in, so we have this definitely some signal underneath this noise. Let's capture this noise with a Brownian motion. And in that middle bullet point there, that's where the DT, that DT part, that's the deterministic part, that's over the time. But the DBT, that's the Brownian motion piece. And you might notice here that there's a DSDT, but there's an ST with the DT, and there's an ST with the DBT. Well, this is called a geometric stochastic differential equation, and can be solved analytically. And in fact, it's just the exponential of this stochastic process, which again has a deterministic piece as well as as that random piece, right, which we assume is captured with the Brownian motion. Well, that's great, but we have an agent option we are trying to price. And unfortunately, with this modeling of the stock price, it doesn't have an analytic solution. So with this in mind, one would want to do some type of Monte Carlo simulation in order to get a better idea of how to exactly price an option. So let's take the example of the strike price being $110, but the current price is $100. How exactly, is this worth anything? The current price is $10 a share less than the strike price. Of course, we are taking the averages. So in order to be able to get a better idea of exactly, to know how, not only if this contract is worth anything, but how much it would be worth. Well, then the figure on the top right shows the random paths, just a tremendous number of random paths taken. To get an idea about exactly how precisely the evolution would be. Of course, we'd have to do this a lot of times, hence the Monte Carlo. And then with all these values taken, one would then be able to get the distribution of these values, and you can see almost a log normal there. And you see a tail on the bottom right. You see a tail with the larger stock prices, and then a bit of a tail, but it's a bit thicker on the bottom on the bottom left with the lower prices. But of course, this is an average. So if you take this average over this time, you can actually see this is actually pretty valuable, and the option is worth $9.23 a share. And so this is precisely why the method that we've derived would be great within this particular use case.
Perfect. Yeah, thanks, Andrew. So in essence, when we're trying to price this Asian option, we're looking at averaging all the possible different prices over the course of the contract. And what this amounts to is that at each point in time, we're looking at a log normal distribution of possible asset prices. So really, that equation at the bottom there, that's saying we really want to take an average of all these log normal distributions, and then compute our payoff function based on that. And so we can think about our conditions in our conditional generator as being each one of these time steps, trying to model all these different log normal distributions. And you can see even at the last time step, that's a fairly heavily skewed log normal because you have a lot of potential upside, 100 time periods in the future. Great. So the next thing we want to go over is the building blocks of quantum Monte Carlo simulations. And so
with some questions that have come in from the chat.
Sure.
So yeah, we have a few questions about the earlier parts. So one is the advantage here only in terms of time, or could there be another kind of advantage in terms of accuracy or generalization with the quantum methods?
Absolutely. So quantum Monte Carlo does have a theoretical speed up in terms of the complexity. So for instance, if you need to take 50,000 samples from a classical Monte Carlo simulation, or simulated 50,000 times, the idea is perhaps with only a few hundred measurements of a quantum circuit, you could achieve the same level of accuracy. So it scales as a square root of the number of classical samples. Now there's a lot of nuance there because you have to factor in wall clock time, and the next slide is going to talk about each one of the components of quantum Monte Carlo and how that impacts that theoretical speed up we hope to achieve.
Cool. And then another couple of questions are quite similar. One person asked, how have you chosen the generator ansatz? And another question is, how was two local circuit identified as the best ansatz?
Yeah, definitely. So we started with a very simple hypothesis and circuit. I wouldn't say that we believe that the current structure of our generator is ideal. There's probably a lot of room for improvement, but we were able to identify, for instance, the two local circuit as a good candidate for a baseline implementation of our method. There may be more specific ansatzes that may be better tailored to this application. And really, for every use case you encounter, there will have to be thoughtful considerations of the exact circuit structure you want to choose. We just decided to go with a very generic one that was easily trained and implemented.
Mm-hmm. Cool. And another question is, can GAN be used for video data generation, and how could quantum GAN help with improving it? It's
an interesting question. I don't know, Andrew, do you have your thoughts on for video?
For the video generation? Not at the moment. Unfortunately, the level of complexity is a little bit out of the range for applications at this moment. But it's something we're definitely thinking about. I mean, when we with our own experiments and research within GANs, we are definitely comparing it against what's possible in classical and going from there. But I imagine that because of the number of data points that are needed to train a robust model, you might be more that because of that, the quantum GAN would definitely give an advantage. But yeah, but no, that is theoretical, but it's a great question, and unfortunately, it's out of reach right now.
Cool. Thanks for answering the questions, and please, please carry on with the presentation.
Okay, great. All right. So I like to think of four main components of conducting Monte Carlo simulations on a quantum computer. The first of which is state preparation. So that's loading or evolving your random variable of interest. In our case, it was how those log normal distributions at every point in time evolve. And that's the one we focused on implementing our circuit to provide an efficiency gain. The second step then is to compare all the possible different asset prices with the strike price. The third step then is to efficiently embed our piecewise linear payoff function into an ancilla qubits amplitude. And the reason for embedding this in a qubits amplitude is that we can perform quantum amplitude estimation to realize the quadratic theoretical speedup in extracting our, the fair price of the option. Now, I'm not going to go into too much detail on amplitude estimation. We do have more detail on our paper, and there's plenty of other material out there to cover it. But in essence, it's an application of Grover's algorithm. And it turns out that you can think of Grover's algorithm as a rotational operator, and whose eigen value of that rotational operator is the angle of rotation. And you can actually use that to get the initial amplitude of the quantum state you're interested in. So again, if you had a quantum circuit and you wanted to know what the amplitude or probability of a certain state was, you would have to, for instance, measure it 50,000 times to get to a certain level of precision. And amplitude estimation allows you to do that and square root the number of samples. So maybe with only a few hundred samples. So that's really why a lot of financial institutions are excited about quantum Monte Carlo simulations. If you, from a complexity standpoint, if you can get your quantities of interest in far less samples, that could be incredibly valuable to these institutions. So now back to state preparation. So especially with the stochastic process, like based on Brownian motion, where for an Asian option, for instance, we have to consider all the possible asset prices over the life of the contract. That can be very difficult to do in a quantum setting. And other research has proposed to, for instance, at each time step, load a distribution on separate registers. And so we could see how that quickly may blow up your number of qubits and number of registers. And so the idea here is either to load them independently or start with one base distribution and then use quantum arithmetic to evolve it to the other distributions. And then finally, you would have to compute the average of all these log normal distributions. And that could be some more quantum arithmetic, which is very expensive. Now, one thing I did want to point out is that we have this theoretical speed up that's possible doing things like pricing derivatives. But each one of these steps could erode that theoretical speed up. And so it's critically important that we take each of these steps and try to maximize how efficient we're implementing them. So for instance, if our state preparation procedure is not efficient or uses too many gates or qubits, that could erode some of the speed up we're hoping to achieve. Or if we have to perform really complicated arithmetic on a quantum computer, that also could erode some of the speed up. So really all of these steps, besides the last one, is to safeguard and protect the speed up that Grover's algorithm has afforded to us. And we believe that using the conditional generator in terms of state preparation is one step to providing that efficiency. So in the next slide, great. So now that we have our condition register, which we've trained now to be, all of our conditions are the different time steps. Now that when we want to go price this Asian option, we can simply put all those conditions in equal superposition to take the simple average of them. Now, you could not just take a simple average. You could have more complicated averages, weighted averages, or whatnot on that condition register. But we can mix those conditions so that we get the desired outcome in the generator register to then continue on with the rest of our algorithm. Now, as far as training our generator, again, we took a fairly straightforward approach where we initialized the condition register to the time step number. We then measured the output of the generator register a number of times. And then we either used gradient or gradient-free classical optimizers to update both the alpha and theta parameters. So in the results I'm going to show next, we did calculate the the gradients for all those parameters using the parameter shift method, which really allowed us to increase the accuracy of the distributions loaded. So in the next slide, great. So for our proof of concept, we did 4 time steps. And you can see some of the results here from how our quantum conditional generator performed learning these different distributions. And now they all may seem kind of similar, but the important point is that these are different log normal distributions. And as the stock evolves throughout the time periods, you're going to have a fatter tail to the right. So the distribution is going to be skewed to the right. And our generator was able to match these specific distributions across the 4 time steps. Again, to keep it simple, and because we're working on a simulator, that's kind of the reason for including a limited number of time steps, but we're definitely excited to expand the number of conditions in this circuit to realize even more of a benefit. Another thing you can notice that while we were fairly accurate with loading these distributions, we weren't perfect. So if you see like the difference between the light blue line and the darker blue bars, there still is definite room for improving not only, again, the variational circuits we use, but the training regime we employed, and everything in between to really get as close as we can to these exact distributions. Okay, so I think the next slide. Yeah, so here are some of the results. And I know the picture is fairly small on the left there, but that's our overall circuit for pricing an Asian option. And so back to our original example, we took an initial stock price of $100, a couple of parameters for the risk-free rate and annualized volatility, strike price of 110, and again, just 4 time steps. So the first 2 qubits up there is our condition register. So we have 2 qubits with 4 time steps, and we put them in superposition to take the average of them. So the generator then is the next 5 qubits, which ends with the 2 local circuit. And then you can see the exact steps that I mentioned before. We have a Qiskit integer comparator that flips an ancilla qubit if the asset price is greater than the strike price. And then we embed our piecewise linear function into that last qubit's amplitude, utilizing controlled Y rotations. And so after this circuit was constructed, we performed amplitude estimation on the last qubit. Now, on the graph there, you can see different fair value prices. And I'd like just to walk through those different prices and why they are different. So if we perform classical Monte Carlo simulations with 50,000 or 100,000 simulations, we would get to a really accurate price of $9.23. Now, in the quantum setting, we're dealing with discretized distributions. So once we move away from continuous distributions of those different asset prices to only 32 intervals with 5 qubits, we get a price of $13.85. So we can think of that as our discretization price, our cost of taking a continuous distribution and making it into only 32 intervals. And then if we look at the exact distributions loaded on the conditional generator, and we analytically calculated the fair value price from those, we get a price of $14.41. And so that difference between the $13 and the $14, that's the cost of our training error. So, our distributions weren't exactly matching the actual real life ones. And so there is some room there to improve and close the gap. But then finally, if we took the distributions that were actually loaded on the register and performed quantum Monte Carlo simulation, we would get the same price of $14.41. And so that confirmed to us that, yes, this procedure with all these steps of quantum Monte Carlo works. There is some room for improvement, but most of the improvement could be extending the number of qubits in the generator register to really get closer and closer to a continuous distribution. Okay, great. So the last thing I just want to cover is, some of the open research questions we have and some of the ideas we're thinking about for next steps. So, and I've listed a few here. Really, the talk today was really trying to just get people thinking about how to take a lot of these different classical models and translate them to the quantum setting. So there is a whole other, a lot of other different kinds of generators or GANs out there. And so it would be great for people to start thinking about how to translate them to the quantum setting and what applications or use cases we could apply them to, like we did today. But specifically, we would love to know what other ansatses to the earlier question provide better performance for this or other learning tasks. What kind of circuit optimizations can further decrease the cost of state preparation? How does our proposed circuit structure scale, and how does it affect the generator performance? For instance, if we had 30 time steps or 50 conditions, how can the circuit structure of the generator still keep up with that many conditions, or what other enhancements do we have to make it feasible? And then finally, really the holy grail of all of this is there a way to, after learning the previous time steps, predict the next one? And so we do think that this framework is a great starting point to start thinking about all of these questions. But really, if we could find a way to predict the next distribution, how that log normal shifts and scales for the next time step, that would be incredibly powerful. And we're looking forward to continuing it. So I'd just like to end that, and hopefully we have some more questions. But the next slide, I just want to end quickly saying, thank you very much. Andrew and I are always enjoy talking with other researchers or people interested in quantum. So please feel free to reach out with any questions, suggestions, or ways we can help.
Cool. Thank you for the talk. Thanks, both of you. It was a really, really nice presentation and very wide-ranging ideas presented there. If anyone has a question, another question, please put them in the chat, and we'll get to them. I also enjoyed the conversation style, worked nicely. So we have one question about the earlier slide. Says, can you please explain in which cases there is quantum benefit regarding the quantum complexity and comparison slide?
Andrew, I think that maybe that's
the quantum benefit regarding the quantum complexity. So definitely this was shown mathematically, and I think we said this a few times throughout the presentation, that quantum neural networks require a lot less data. And one reason for that, and intuitively, you have one parameter per operator. And even for a controlled operator, for example, and that encompasses 4x4 or a 16x16 matrix. Instead of learning for every single one of those parameters, you just essentially have one to learn for. So intuitively, that's the way to think about that. And that gives you a huge advantage. I mean, everybody's focusing on large data problems. Well, what about small data problems? It's only information you have. You got to extract information out of it. How do you do that? And in a manner to really optimize information that's there and not be biased and separate that signal from the noise. So that would be so for quantum and from that perspective would definitely be that advantage. Also, as was noted with the Kukatani fixed point theorem, if your algorithm, right, not the variational piece, of course, but if your algorithm is strictly within a quantum circuit, then your state space is convex, and you only have one optimal point instead of a lot of local optimal points, right? Which you suck in those energy wells, which are suboptimal and really don't get you down to that optimal, that optimal point to really give you the most robust statistical model that you can possibly get out of the information that you're feeding it through the data. And having been at Bank of America, I guess that gives me a little bit of PTSD because the regulators are like, anytime you make any changes to those parameters, you got to do it. It's going to kick off a whole 2 months of regulatory administrative work. So I try to get the most as I can out of the model, so I don't have to completely keep retraining it every time. So so I guess under those two examples of low data and also having a strictly quantum circuit algorithm, then you really do see that advantage right away.
Cool, thanks. Yeah, if anyone has any final questions, then pop them in the chat. Otherwise, we'll start wrapping up. We had lots of questions along the way. Yeah, so just to thanks everyone for joining us. And again, we'll have this seminar continuing next week at 12 p.m. Eastern time again. Next week, we're going to have Young-Seok Kim and Andrew Eddins from IBM Quantum speaking about the evidence for the utility of quantum computing before fault tolerance. Should be an interesting seminar, so please tune in for that if you're interested. And yeah, we have a question checking if the paper is conditional generative models for learning stochastic processes, which I believe it is. But yeah, so yeah, that is the paper that this presentation was about. So lots more information there for getting the details. And yeah, Andrew or Sal, do you have any final comments for our audience before we finish?
I don't think so. Thanks, Maria.
Yeah, I would just like to reiterate what Sal said at the end of the presentation. We're always happy to talk quantum. We're really super interested in the science and applications, so please don't be afraid to reach out.
Great, thanks. So we've got lots of nice comments coming in the chat saying thank you for the discussion, excellent presentation, thank you for the presentation. So yeah, looks like lots of people enjoyed it. So thank you all for joining us today, and we will see you next time. Bye.